Welcome to my video on factorial designs. This is an important topic for us to cover since almost all experiments in psychology are factorial designs. A factorial design is just an experiment with more than one independent variable. This is an experiment on the effects of hours of studying and hours of sleep on exam performance. This experiment is a 2x2 factorial design. A 2x2 factorial design is an experiment with two independent variables, each of which have two levels. In this experiment, the first independent variable is hours of studying. The two levels are 10 hours and 20 hours. The second independent variable is hours of sleep. The two levels are 4 hours and 6 hours. Up here, this number is the number of levels of IB1, and this number is the number of levels of IB2. If you multiply the number of levels of IB1 by the number of levels of IB2, you get the total number of conditions. 2 times 2 equals 4, so a 2x2 factorial design has 4 conditions. These 4 boxes are the 4 conditions in my experiment. In a factorial design, each condition is called a cell, so these 4 conditions are the 4 cells in my experiment. I started with 8 participants, and I assigned 2 participants to each of the 4 cells. I recorded each participant's exam score, so the dependent variable is exam score. In a factorial design, the mean of each cell is called a cell mean. I calculated each of these cell means by adding the 2 values in each cell and dividing the total by 2. The row and column means are called marginal means. The marginal mean of column 1 is the mean of all 4 values in column 1. The marginal mean of column 2 is the mean of all 4 values in column 2. The marginal mean of row 1 is the mean of all 4 values in row 1. The marginal mean of row 2 is the mean of all 4 values in row 2. The difference between the two column means is the main effect of IB1. If the two column means are equal, then there's no main effect of IB1. If the two column means are not equal, then there is a main effect of IB1. These two column means are not equal, so our data is showing a main effect of IB1. We can look at the main effect of IB1 in a graph. This graph is showing the two column means. We can see that the mean exam score of the 4 people who studied 20 hours is 20 higher than the mean exam score of the 4 people who studied 10 hours. This graph is showing the main effect of IB1. The difference between the two row means is the main effect of IB2. If the two row means are equal, then there's no main effect of IB2. If the two row means are not equal, then there is a main effect of IB2. These two row means are not equal, so our data is showing a main effect of IB2. We can look at the main effect of IB2 in another graph. This graph is showing the two row means. We can see that the mean exam score of the 4 people who slept 6 hours is 30 higher than the mean exam score of the 4 people who only slept 4 hours. This graph is showing the main effect of IB2. This diagonal line right here is the main effect of IB1. If the two column means had been equal, then this line would have been flat, and we would have had no main effect of IB1. This diagonal line is the main effect of IB2. If the two row means had been equal, then this line would have been flat, and we would have had no main effect of IB2. A factorial design allows you to look at the main effects of the two independent variables, but it also allows you to look at whether the effect of each independent variable depends on the level of the other independent variable. If the effect of each independent variable depends on the level of the other independent variable, then there's an interaction between the two independent variables. Let's look at whether we have an interaction in this data set. Let's start by looking at whether the effect of IB1 depends on the level of IB2. In the 4-hour condition, the mean exam score of the 2 people who studied 20 hours is 20 higher than the mean exam score of the 2 people who studied 10 hours. In the 6-hour condition, the mean exam score of the 2 people who studied 20 hours is 20 higher than the mean exam score of the 2 people who studied 10 hours. So in row 1, this mean is 20 higher than this mean, and in row 2, this mean is also 20 higher than this mean. We can see that the effect of hours of studying is the same in row 1 that it is in row 2. So the effect of hours of studying doesn't depend on the level of hours of sleep. Now let's look at whether the effect of hours of sleep depends on the level of hours of studying. In the 10-hour condition, the mean exam score of the 2 people who who slept 6 hours is 30 higher than the mean exam score of the 2 people who only slept 4 hours. In the 20-hour condition, the mean exam score of the 2 people who slept 4 hours is also 30 higher than the mean exam score of the 2 people who only slept 4 hours. So in column 1, this mean is 30 higher than this mean, and in column 2, this mean is also 30 higher than this mean. So the effect of IB2 in column 1 is the same as the effect of IB2 in column 2. So the effect of IB2 doesn't depend on the level of IB1. What we can see here is that the effect of IB1 doesn't depend on the level of IB2, and the effect of IB2 also doesn't depend on the level of IB1. That means that there's no interaction between these two independent variables. If we make a graph, we can see that there's no interaction. To look at whether there's an interaction or no interaction, we need to make another type of line graph that plots the 4 cell means, and I'll show you how to make that type of graph. First, we have to choose which variable to put on the x-axis. We could either put hours of studying on the x-axis, or we could put hours of sleep on the x-axis. The variable that we choose to put on the x-axis won't affect whether or not we see an interaction. I decided to put hours of studying on the x-axis. So above the 10-hour tick mark, I plotted the 2 cell means in the 10-hour column, 47 and 77. Above the 20-hour tick mark, I plotted the 2 cell means in the 20-hour column, 66 and 97. Now what we need to do is we need to make a line connecting the 2 cell means in row 1 in the 4-hour condition. We also need to make another line connecting the 2 cell means in row 2 in the 6-hour condition. Here we can see that this goes up by 20, and this also goes up by 20. So that's why the effect of IB1 doesn't depend on the level of IB2. This is 20 higher than this, and this is also 20 higher than this. We can also see here that this is a difference of 30, and this is also a difference of 30, which is why the effect of IB2 doesn't depend on the level of IB1. This is 30 higher than this, and this is 30 higher than this. So this graph is showing that there's no interaction between the 2 independent variables. It's showing that the effect of each independent variable doesn't depend on the level of the other independent variable. Whenever there's no interaction between the 2 independent variables, the 2 lines end up being parallel, like they are here. If we found this outcome, our conclusion would be that if you study 20 hours, you'll do better than someone who only studied 10 hours, regardless of how much sleep you had. I made some labels to show that this line is connecting the 2 cell means in the 4-hour row, and this line is connecting the 2 cell means in the 6-hour row. This graph is showing that there's no interaction between the 2 independent variables, but this graph is also showing the main effects of the 2 independent variables, and I'll explain why. We know that the mean exam score of all 4 people who studied 10 hours is 62. That marginal mean of 62 is halfway between these 2 cell means that I plotted above 10 hours. It's halfway between 47 and 77. We know that the mean exam score of all 4 people who studied 20 hours is 82. That marginal mean of 82 is halfway between these 2 cell means that I plotted above 20 hours. It's halfway between these 2 cell means of 67 and 97. If I drew a line connecting this marginal mean of 62 with this marginal mean of 82, I would have a third line in this graph showing the main effect of hours of studying. It would be halfway between these 2 lines. So that's why this graph does show the main effect of IB1. Now I'll explain why this graph is showing the main effect of IB2. We know that the mean exam score of all 4 people who slept 6 hours is 87. That marginal mean of 87 is at the center of this line right here, halfway between 77 and 97. You know that the mean exam score of all 4 people who slept 4 hours is 57. That marginal mean is at the center of this line, halfway between 47 and 67. If we drew a line connecting the marginal mean of 57 to the marginal mean of 87, that vertical line would be showing the main effect of IV2. So basically, the fact that this 6-hour line is higher than this 4-hour line shows that we have a main effect of IV2, in which the people who slept 4 hours did better overall on the exam than the 4 people who only slept 4 hours. Now let's look at a different data set in which there is an interaction between the two independent variables. This is the same experiment, but I changed the numbers in the data set. Now, these two lines are not parallel because these two cell means are both 47. So there's no difference between the two cell means in row 1, which is why this line is flat. But in the second row, this mean is 20 higher than this mean, which is why this line is dropping from 97 down to 77. This data set is showing an interaction between the two independent variables because it's showing that the effect of IV1 depends on the level of IV2. In the 4-hour condition, hours of studying has no effect because these two cell means are equal. These two people who studied 20 hours had the same mean exam score as these two people who only studied 10 hours. In the 6-hour condition, hours of studying did have an effect because these two people who studied 20 hours got a mean exam score of 97, but these two people who only studied 10 hours got a mean exam score of only 77. This mean was 20 higher than this mean. So right here we have the difference of 0, which is row 1, and here we have the difference of 20, which is row 2. So this graph is showing an interaction, and we can tell that there's an interaction because the lines are not parallel. If we ended up with this outcome, our conclusion would be that if you don't get enough sleep, studying 10 more hours won't help you to get a better exam score on average, because these two people had the same mean exam score as these two people over here. We would also conclude that if you do get a decent amount of sleep, then studying 10 more hours will help you on the exam because these two people had a mean exam score that was 20 higher than the mean exam score of these two people. And we can also see the main effects up here. We can see that the mean of the 20-hour column is higher than the mean of the 10-hour column. So overall, people who did more studying did better. And we can see the main effect of IV2 right here. We can see that the 4 people who got 6 hours of sleep did better overall than the 4 people who only got 4 hours of sleep. But the most interesting outcome in this data set is the interaction right here, which shows that in the 6-hour condition, hours of studying did have an effect, and in the 4-hour condition, hours of studying didn't have an effect. In all of the examples that we looked at so far, we've had a main effect of IV1 and a main effect of IV2. Now let's look at an example in which one of the two main effects is missing. I changed the numbers so that we have a new data set. In this data set, the mean exam score of the 4 people who studied 10 hours is 62, and the mean exam score of the 4 people who studied 20 hours is also 62. Since the two column means are equal, there's no main effect of IV1. Overall, the people who studied 20 hours performed the same on the exam as the people who studied 10 hours. That's why there's no main effect of hours of studying. But the two column means are different. The 4 people who slept 6 hours had a mean of 77, and the 4 people who slept 4 hours had a mean of only 47. So since this mean is 30 higher than this mean, we do have a main effect of IB2, which is hours of sleep. So there's no main effect of IB1, but there is a main effect of IB2. In this third graph that's showing the cell means, we can look at whether there's an interaction. The 2 cell means in the 4-hour row are both 47. They're both equal. And in the 6-hour row, the 2 cell means are both 77, so they're both equal. Since these 2 lines are parallel, there's no interaction between the 2 independent variables. The effect of IB1 doesn't depend on the level of IB2 because there's a 0 difference in row 1 and there's also a 0 difference in row 2. The effect of IB2 also doesn't depend on the level of IB1 because these 2 cell means in column 1 are 30 apart. I mean, this one is 30 higher than this one, and these 2 cell means in this column are also 30 apart. This one is 30 higher than this one. So here we have a difference of 0 going across, and we have a difference of 0 going across. Here we have a difference of 30, and here we also have a difference of 30, which means that the 2 lines are parallel and there's no interaction. The effect of each independent variable doesn't depend on the level of the other independent variable. So here we have an example in which there's no main effect of IB1, there is a main effect of IB2, and there's no interaction. You can actually tell that there's no main effect of IB1 and that there is a main effect of IB2 just by looking at this third graph that shows the cell means. And I'll explain how you can tell that there's no main effect of IB1 and that there is a main effect of IB2 just by looking at these cell means. This marginal mean of 62, which is the mean of all 4 people who studied 10 hours, is halfway between these 2 cell means right here, above 10 hours. This marginal mean of 62, which is the mean of all 4 people who studied 20 hours, is halfway between these 2 cell means that are above 20 hours. So here we have the marginal mean of 62 for the 10-hour condition, and here we have the marginal mean of 62 for the 20-hour condition. If you connected those 2 marginal means and made a third line in this graph, the line would be flat, which means that there's no main effect of IB1. There's no main effect of hours of studying. This marginal mean of 47, which is the mean of all 4 people who slept 4 hours, is the center of the 4-hour line right here. This marginal mean of 77, which is the mean of all 4 people who slept 6 hours, is at the center of the 6-hour line. So here we have the marginal mean of 47, and here we have the marginal mean of 77. If we connected those 2 marginal means with a vertical line, we would see a difference. We would see a difference of 30 right here. So since this line would be flat, there's no main effect of IB1, but there's no difference going from left to right. But since there is this vertical distance of 30 right here, there is a main effect of IB2. Let's now look at another example. I changed the numbers again. This time, the 2 column means are different. This column mean is 20 higher than this column mean. So there is a main effect of IB1. We can see that main effect right here in the top graph. But the 2 row means are equal. They're both 67. So there's no main effect of IB2. There's no main effect of hours of sleep. And down here, we have 2 lines that are not parallel, so there is an interaction. In row 1, in the 4-hour condition, the mean of the 2 people who studied 20 hours is 40 higher than the mean of the 2 people who only studied 10 hours. which is a large effect of hours of studying. But in the second row, in the 6-hour condition, the mean of the two people who studied 20 hours is equal to the mean of the two people who only studied 10 hours. So what we have is we have a big effect of hours of studying in the 4-hour condition, but no effect of hours of studying in the 6-hour condition. We do have an interaction because the effect of hours of studying in row 1 is 40. It's a difference of 40. But the effect of hours of studying in row 2 is 0 because there's no difference. We can see that right here. And we can see that the 6-hour line is flat because there's no difference between these two cell means. And we can see that the 4-hour line is dropping down by 40 because this cell mean is 40 higher than this cell mean. Here we have an interaction in which the two lines cross. The two lines don't have to cross for there to be an interaction. They can cross, but they don't have to. The word interaction doesn't mean that the lines have to physically interact. So the word interaction doesn't actually have anything to do with whether the two lines are physically interacting. Let's look at the two main effects. Here we have a main effect of IV1. Here we have no main effect of IV2. So what I've shown you here is a data set in which one of the two main effects is missing, and we do have an interaction. Now let's look at an example of a data set with an interaction but no main effects. I changed the numbers, so this is a new data set. In this data set, the two column means are equal, so there's no main effect of IV1. The two row means are also equal, so there's no main effect of IV2. The lines connecting the cell means are not parallel. They're forming an X, which means that there is an interaction. Whenever the lines that are connecting the cell means form an X, there's no main effects. There's no main effect of IV1, and there's no main effect of IV2. Let's look at this table over here to help us understand why these two lines are forming an X. In the 4-hour condition, the 10-hour mean is 47, and the 20-hour mean is 87. So when you go from this mean to this mean, you're going up by 40. That's why the 4-hour line starts at 47 and goes up by 40. It rises by 40. In the 6-hour condition, the 10-hour mean is 87, and the 20-hour mean is 47. When you go from this mean to this mean, you're going down by 40. That's why the 6-hour line starts at 87 and then goes down by 40, down to 47. So when you go from the left to right, the 4-hour line is going up by 40. That's because this is going up by 40 right here. The 6-hour line is going down by 40. That's because this is going down by 40 right here. Here we have an interaction in which the effect of IV1 in the first row is the opposite of the effect of IV1 in the second row. In the first row, the effect goes up by 40, and in the second row, the effect goes down by 40. If we got this outcome, it would suggest that if you've only had 4 hours of sleep, doing more studying will help you, but if you've had 6 hours of sleep, doing more studying will actually hurt you on the exam. It would be really strange to get this type of outcome in our data set, and I don't think I would expect this type of outcome in this study, but I just wanted to show it to you to give you an example of a data set with an interaction but no main effects. This is a special type of interaction because the effect of IV1 in the first row and the effect of IV1 in the second row cancel each other out, and there ends up being no main effect of IV1 down here. And the effect of IV2 in the first column and the effect of IV2 in the second column also cancel each other out, and there ends up being no main effect of IV2 over here. Sometimes this is called an antagonistic interaction because the two main effects are both canceled out, and there ends up being no main effect of IV1 and no main effect of IV2. Now I want to show you a summary of the different types of outcomes that can be found in a 2x2 factorial design. In the top row, we have 3 examples of an interaction. This one is an interaction with no main effects. This one is an interaction with 1 main effect. And this one is an interaction with 2 main effects. In the bottom row, we have 3 examples of no interaction. If the 2 lines are both flat, and they're both right on top of each other like they are here, there's no interaction and no main effects. If one line is above the other line, but they're both flat, there's no interaction and 1 main effect. If one line is above the other line, and they're both going in the same direction, from left to right, and they're both parallel like they are here, then there's no interaction and 2 main effects. Notice how in all 3 of these graphs, the 2 lines are not parallel. That's why all 3 of these are interactions. Notice how in all 3 of these graphs, the lines are parallel. That's why all 3 of these are examples of no interaction. When the lines are not parallel, there's an interaction, and when the lines are parallel, there's no interaction. Now I want to show you an example of a different data set that I think would show an interaction. This is a different experiment. In this experiment, I'm still recording exam scores, but now my first independent variable is alcohol intake. Half the participants are getting no alcohol, and the other half of the participants are getting alcohol. My other independent variable is food intake. Half the participants are getting food, and the other half of the participants aren't getting food. What I would probably expect to see is that when the participants have alcohol on an empty stomach, they'll do the most poorly on the exam, and the average will be low. And I would expect that when the participants are eating food and they're having alcohol on a full stomach, they won't do so poorly on the exam because the alcohol won't affect them as much. So here we have participants who have no food and no alcohol. They did pretty well on the exam because the mean is an 87. But when the participants have no food and alcohol, this mean drops down quite a bit because they're having alcohol in an empty stomach. When the participants have food and no alcohol, they still do pretty well on the exam, like they did up here. And when participants have food and alcohol, the mean drops, but it doesn't drop by as much as it did in the top row, because in this bottom row, the alcohol isn't affecting people as much because they're having the alcohol on a full stomach. So in the no food condition, the mean exam score drops by 40 when the participants have alcohol, but in the food condition, the mean only drops by 10 when the participants have alcohol. So the effect of alcohol in the no food condition isn't the same as the effect of alcohol in the food condition, which means that there's an interaction between these 2 independent variables. The effect of IV1 is changing across the levels of IV2. That's why these 2 lines are not parallel down here. This steep line is the difference between these 2 cell means in the no food condition, where the mean drops down by 40. This shallow line right here is the effect of alcohol in the food condition. This line only drops by 10, because in the food condition, the mean only drops by 10 when the participants have alcohol. So here we have a steep effect of alcohol on an empty stomach, and here we have a more shallow effect of alcohol on a full stomach. So the 2 lines are not parallel, so there is an interaction. Up here we can look at the main effects. We see that the 2 column means are different, so there is a main effect of alcohol intake. The mean of the 4 people who had alcohol is lower than the mean of the 4 people who didn't have alcohol. We also see a main effect of IV2, in which the mean of the 4 people who had no food is lower than the mean of the 4 people who did have food. So in this experiment, alcohol did lower people's exam performance overall, and having no food did lower people's exam performance overall also. The most interesting outcome is this interaction, in which the effect of alcohol was steeper on an empty stomach and less steep on a full stomach. I want to show you one other example of an experiment that I think would show an interaction. In this experiment, the dependent variable is chosen music volume. In this experiment, I'm telling each participant that I'm going to be playing music, and I ask each participant to select the volume that he or she would like the music to be played at. I have two independent variables. The first independent variable is stress level, and the two levels are low and high. The four participants in the high stress condition are having some type of stressful experience during the experiment, and the four participants in the low stress condition are not having that stressful experience during the experiment. The second independent variable is type of music, and the two levels are relaxing and not relaxing. In the relaxing music condition, the participants are told that they'll be listening to relaxing music. In the not relaxing condition, the participants are told that they'll be listening to music that's not relaxing. In the not relaxing condition, I would expect the participants in the high stress condition to choose a low volume, because if they're highly stressed, they don't want to be listening to loud music that's not relaxing. So that's why I think this mean would be such a low number. They'd be choosing a low volume. And in the relaxing condition, I would expect participants who are highly stressed to also choose a lower volume, but I wouldn't expect the effect to be as large, because they're being told that the music is relaxing. So here I would expect a large drop from the low stress condition to the high stress condition. I would expect a large drop in chosen volume. In the relaxing condition, I would also expect a drop in chosen volume, but I wouldn't expect it to be as much of a drop, because when you're told that you'll listen to relaxing music, you might be willing to tolerate a higher volume of music, even though you're stressed. So here we can see the interaction. In the relaxing music condition, the mean chosen volume is dropping down by 1.5. We can see that drop right here. And in the not relaxing condition, the mean of the chosen volume is dropping down by 3.5, which we can see by the steeper line right here. So since this is a bigger drop than this is, there's an interaction between the two independent variables. There's one point that I wanted to make before we move on. In a factorial design, the number of values inside each cell has to be equal. In all of the examples I've gone over so far, I've had 2 values inside each cell. I've had 2 values here, 2 values here, 2 values here, and 2 values here. I could have had 3 values inside each cell if I wanted to, or I could have had 4 values inside each cell if I wanted to, as long as I had an equal number of values inside each cell. I wouldn't be allowed to have 3 values in this cell and only 2 values in this cell. And I think it'll make sense why that's true if we go back to look at this experiment back here. Let's imagine that instead of assigning 2 people to each cell, I assigned 3 people to this cell, only 1 person to this cell, and 2 people to this cell, and 2 people to this cell. So it's 3, 1, 2, 2. If I did that, then my no alcohol condition would include 3 people who had no food, and my alcohol condition would only include 2 people who had no food. That would confound the difference between these two column means. It would either make the difference between these two column means larger or smaller than it would otherwise be. And I don't want the main effect of alcohol intake to be confounded, so I have to make sure that the no alcohol condition has 2 people with no food, and 2 with food. And the alcohol condition also has 2 with no food and 2 with food. So what I need to have is I need to have a balanced experiment. We talked about balancing a little while back. If half of the no alcohol condition is no food and the other half is food, and the half of the alcohol condition is no food and the other half is food, then this variable of food intake is balanced across these two conditions, and this main effect is not confounded. Also, I need for the no food condition to be half no alcohol and half alcohol, and for half of the food condition to be half no alcohol, half alcohol. That way, this variable of alcohol intake is also balanced across the two rows, and this main effect of food intake is also not confounded. So if you have an equal number of people in each cell, the experiment is balanced, which means that the main effect of IV1 is not confounded, and the main effect of IV2 is also not confounded. But if you have unequal values in each cell, the main effects will be confounded, and you won't be able to interpret the main effects anymore. You would still be able to interpret the interaction, but the main effects would be confounded. Let's now go over the different ways to run the participants through the cells of a factorial design. One type of factorial design is a between subjects factorial design. In a between subjects factorial design, each cell has a different group of people. In this experiment right here, I randomly assigned 1/4 of my participants to each cell. I had a total of 16 participants, and I randomly assigned 4 of them to each cell. And each participant was tested one time only. Another type of factorial design is a within subjects factorial design. In a within subjects factorial design, each participant goes through all of the cells of the experiment. So notice how I put person 1, person 2, person 3, person 4 into each of the cells. What I'm trying to show you is that the same group of 4 people is inside each of these 4 cells. Person 1 goes through all 4 cells, person 2 goes through all 4 cells, and persons 3 and 4 also go through all 4 cells. Each participant is tested 4 times. And in a within subjects factorial design, you have to counterbalance the conditions. What I could do in this experiment is use a Latin square, because I actually have 4 conditions, which means that I probably can't do complete counterbalancing. In other words, I probably can't use every possible order of conditions because there's too many possible orders. But what I can do is use a Latin square to select these 4 orders right here. And then I can randomly assign one of my participants to each of these 4 orders. So person 2 was assigned to the A, B, D, C order, which means that person 2 will get condition A at time 1, which is this cell, condition B at time 2, which is this cell, D at time 3, which is here, and C at time 4, which is here. I assigned person 1 to B, C, A, D, which means that person 1 will get condition B at time 1, C at time 2, which is right here, A at time 3, which is right here, and D at time 4, which is right here. Participant 3 was assigned to C, D, B, A, which means they get C at time 1, D at time 2, B at time 3, and A at time 4. And participant 4 was assigned to D, A, C, B, which means the time 1 here, time 2 here, time 3 here, and time 4 here. So this was this is the counterbalancing that I used. Another type of factorial design is called a within set. Another type of factorial design is called a mixed factorial design. In a mixed factorial design, either each participant is assigned to one column or the other and goes through both rows, or a participant is assigned to one row or the other and goes through both columns. So in this example right here, I had 8 total participants. I assigned 4 of them to the 4-hour condition, which is this row right here, and I assigned 4 of them to the 6-hour condition, which is this row right here. And then these 4 participants were tested twice. One time with 4 hours of sleep and 10 hours of studying, and one time with 4 hours of sleep and 20 hours of studying. So these are the 2 scores from person 1. These are the 2 scores from person 2, and so on. These 4 participants were assigned to the 6-hour condition. Each of these 4 participants were also tested twice. One time with 6 hours of sleep and 10 hours of studying, and one time with 6 hours of sleep and 20 hours of studying. So here's the first score from person 5. Here's the second score from person 5. So each participant was assigned either 4 hours or 6 hours of sleep, and each participant experienced both taking a test with 10 hours of studying and taking a test with 20 hours of studying. So since each participant experienced both the 10-hour condition and the 20-hour condition, I needed to counterbalance the 10-hour and 20-hour conditions. So here's the counterbalancing that I used in this experiment right here. 10 hours is condition A, 20 hours is condition B. Person 1 was assigned to the A-B order because they had 10 hours at time 1 and 20 hours at time 2. So for person 1, this score was recorded at time 1. This score was recorded at time 2. Person 2 was assigned to the BA order, which meant this person studied 20 hours at time 1 and 10 hours at time 2. So for person 2, this score was at time 1, this score was at time 2. So person 2 went through these 2 conditions in the opposite order. Person 1 went through 10 hours, then 20 hours. Person 2 went through 20 hours and then 10 hours. So each of my participants was assigned to either the AB order or the BA order. 4 of them were assigned to AB, and 4 of them were assigned to BA, because I have to make it equal. So let's look at some other people down here. In the 6-hour condition, person 7 was assigned to the AB order, because this score was time 1, this score was time 2. Person 8 was assigned to BA, because this score was time 1, this was time 2. So each participant took the test 2 times, one time with 10 hours of studying and one time with 20 hours of studying, but half of them did 10 hours first and 20 hours second. The other half did 20 hours first and 10 hours of second. But all of these participants in the top row slept 4 hours at time 1 and 4 hours at time 2. Each of these 4 participants slept 6 hours at time 1 and 6 hours at time 2. Here's a different example of a mixed factorial design. In this experiment right here, each participant is assigned to either the 10-hour condition or the 20-hour condition, and each participant goes through both the 4 hours of sleep and the 6 hours of sleep. So these 4 people right here, person 1, 2, 3, and 4. They're all tested twice. One time they're tested with 10 hours of studying and 4 hours of sleep. The other time they're tested with 10 hours of studying and 6 hours of sleep. These other 4 people are also tested twice. One time with 20 hours of studying and 4 hours of sleep, and one time with 20 hours of studying and 6 hours of sleep. So each participant is assigned to one column or the other and goes through both rows. So since each participant is going through both the 4-hour condition and the 6-hour condition, these two conditions have to be counterbalanced. So here we can see person 1 is AB. So person 1 went through the 4-hour condition at time 1 and the 6-hour condition at time 2. Person 1 took the test at time 1 with 4 hours of sleep and took the test at time 2 with 6 hours of sleep. Person 2 was assigned to BA. So person 2 took the test with 6 hours of sleep at time 1 and with 4 hours of sleep at time 2. They were tested in the opposite order. So I told you that in a mixed factorial design, there's two ways to set up the experiment. Either you can assign each participant to one row or the other and have them go through both columns, like we did here. Or you can assign each participant to one column or the other and have them go through both rows, like we did here. They're both considered mixed factorial designs. A mixed factorial design has certain advantages over a between subjects factorial design, or a within subjects factorial design. One major disadvantage of a between subjects factorial design is that it requires a large number of participants. You need a large number of participants in a between subjects factorial design because you need a separate group of people for each cell of the experiment. A mixed factorial design doesn't require as many participants as a between subjects factorial design because in a mixed factorial design, you're assigning one group to one column and another group to another column, or you're assigning one group to one row and another group to a different row. So instead of needing 4 groups of people, you would only need 2 groups of people to do a 2 by 2 factorial design. One major disadvantage of a within subjects factorial design is that you're testing each person a large number of times because each person has to go through all cells of the experiment. In a 2 by 2 factorial design, there's 4 conditions, which would mean that each person would have to be tested 4 times in a within subjects factorial design. When each person is tested a large number of times, the effects of fatigue can start to become dramatic eventually, which can start to possibly skew the results of the experiment. A mixed factorial design doesn't have that problem because each participant doesn't have to go through all cells of the experiment. Each person has to go through the 2 rows or through the 2 columns, but not through all cells of the experiment. Now we've covered the difference between a between subjects, a within subjects, and a mixed factorial design. In the between subjects factorial design, each person was tested once. In the within subjects factorial design, each person was tested 4 times. And in the mixed factorial design, each person was tested twice. Each of the examples that we go over in the rest of the video will be between subjects factorial designs, in which there's a separate group of people inside each cell. I just wanted to cover these types of designs before we moved on. Now let's move on to talk about a 3 by 2 factorial design. A 3 by 2 factorial design has 2 independent variables. The first independent variable has 3 levels, and the second independent variable has 2 levels. This number is the number of levels of IV1, and this number is the number of levels of IV2. 3 times 2 is 6, so a 3 by 2 factorial design has 6 conditions. In other words, a 3 by 2 factorial design has 6 cells. I started with 12 participants in this experiment, and I randomly assigned 2 people to each of the cells. Just like before, each cell mean is the mean of the cell. This cell mean of 46 is the total of these two numbers divided by 2. This cell mean of 56 is the total of these two numbers divided by 2. Just like before, the marginal means are the column means and the row means. In a 3 by 2 factorial design, I have 3 column means and 2 row means. So this is the mean of all 4 people in column 1. This is the mean of all 4 people in column 2. This is the mean of all 4 people in column 3. This is the mean of all 6 people in row 1. And this is the mean of all 6 people in row 2. In a 3 by 2 factorial design, the main effect of the first independent variable is the difference between all 3 column means. If all 3 column means are equal, then there's no main effect of IV1. For example, if these were 61, 61, and 61, then there would be no main effect of IV1, because they would all be equal. If at least one column mean is different than the others, then there is a main effect of IV1. In this data set, all 3 column means are different, so there is a main effect of IV1. But if it had been something like 61, 61, 71, there still would have been a main effect of IV1 because one column mean would have been different from the other 2. In a 3 by 2 factorial design, the main effect of IV2 is just the difference between the 2 row means, just like it was in a 2 by 2 design. If the 2 row means are equal, there's no main effect of IV2. If the 2 row means are not equal, there is a main effect of IV2. In this graph over here, we can see the main effect of IV1. These are just the 3 column means. We can see that people's exam scores or the mean exam score is increasing as people are doing more studying. This graph right here is showing the main effect of IV2. It's just showing the 2 row means. It's showing that the mean of the 6 people who studied 6 hours is higher than the mean of the 6 people who only studied 4 hours in the top row. This graph down here is showing an interaction, is showing whether there's an interaction. These are the 6 cell means. This line down here at the bottom is connecting these 3 cell means in the 4-hour condition. 46, 56, and 66. This line up here is connecting the 3 cell means in the bottom row in the 6-hour condition. And we can see that there's no interaction because the 2 lines are parallel. The effect of hours of studying is the same in the 4-hour condition as it is in the 6-hour condition. In the 4-hour condition, it goes up 10 at a time, and in the 6-hour condition, it also goes up 10 at a time. So the 2 lines are parallel. We can see that the effect of hours of studying doesn't depend on hours of sleep. So since the effect of IV1 doesn't depend on the level of IV2, there's no interaction. I wanted to show you one other example of a data set that would have no interaction. I changed the numbers, so now this is a different data set. Here we have a graph in which this line is flat, and this line rises, and this line is also flat, and then rises. These 2 lines would actually be considered parallel, because this entire line looks the same as this entire line. These 2 lines match each other, which means that this actually would be no interaction. You can think of it this way. These 2 lines are parallel right here, and these 2 lines are parallel over here, which means that there's no interaction. We have a main effect of IV1 because one column mean is different than the other 2, and we have a main effect of IV2 because the 2 row means are different. Now let's look at an example of a 3 by 2 factorial design that does have an interaction. Here, these two lines are not parallel, because here we have a line that is flat and then goes up, and here we have a line that's completely flat. In order to understand why this is an interaction, you have to think of this entire line as just one line instead of two connected lines. You also have to think of this entire line as just being one line. If you think of it that way, then you'll see that this line has a bend in it, and this line is just flat, which means that the two lines are not parallel, and there is an interaction. Let's look at another example. Well, that was my last example, actually. So here, we just have a summary of some different types of outcomes. These three graphs are examples of a 3x2 design with an interaction. Here the lines aren't parallel, so there's an interaction. Here they're not parallel, so there's an interaction. And here they're not parallel again, so there's an interaction. These three graphs are all examples of no interaction. Here, we obviously have parallel lines. There's no interaction. Here there's no interaction again. Like I said, you could think of it as these two were parallel, and these two were also parallel. This is no interaction also because both lines are flat and they're obviously parallel. Just like before, the cell means are just the means of the cells. I calculated each of these 8 cell means by adding the two values inside of the cell and dividing the total by 2. We talked about how in an experiment with 2 independent variables, you can find a main effect of IV1, a main effect of IV2, and an interaction. In an experiment with 3 independent variables, there's another type of result that can be found called a three-way interaction. And I'll explain what that is. Well, right here, we have the definition. A three-way interaction is a result in which the interaction changes across the levels of the third independent variable. When I plotted these 4 cell means in a graph, I saw an interaction right here. But when I plotted these 4 cell means in a graph, I didn't see an interaction. So what we have is we have an interaction between studying and sleep at the first level of IV3 in the 0 milligram condition, but we have no interaction between studying and sleep at the second level of IV3 in the 100 milligram condition. So the interaction does change from the first level of IV3 to the second level of IV3. Because at the first level of IV3, there is an interaction, and at the second level of IV3, there's no interaction. This entire result here that we see in both of these graphs would be called a three-way interaction. The fact that this graph doesn't look the same as this graph means that we're seeing a three-way interaction. And let's try to understand what this three-way interaction is telling us. What we're seeing over here in the 0 milligram condition is that when the participants are not getting enough sleep, then they do poorly on the exam, regardless of whether they study 10 hours or 20 hours, because they can't think clearly. That's why these two means are both 56, and that's why this line is flat right here. But when the participants get 6 hours of sleep, and they do have a decent amount of sleep, then the extra studying does help them. That's why this mean is 96, and this mean is only 76. It's because these two participants right here benefited from the extra studying. That's why this line drops down by 20 from 96 down to 76. Remember, this is the 0 milligram condition. Over here in the 100 milligram condition, these participants who are not getting enough sleep might actually benefit from the extra studying because the caffeine wakes them up and they can think clearly during the exam. So it could be that in the 100 milligram condition, the participants who sleep only 4 hours benefit from the extra studying, And the participants who sleep 6 hours also benefit from the extra studying. And that's what we're seeing here. When in the 100 milligram condition, the participants who are sleeping 4 hours do better when they have 20 hours of studying. And the participants who sleep 6 hours do better when they have 20 hours of studying. Both rows do better with more studying. That's why the 4-hour line is going up by 20, and the 6-hour line is also going up by 20, and the lines are parallel. The main difference between these two graphs is this fourth dot right here. In the 0 milligram condition, the combination of this combination of 4 hours of sleep and 10 hours, this combination of 4 hours of sleep and 20 hours of studying doesn't lead to good performance because they're sleep deprived and there's no caffeine to wake them up, so they do poorly right here. But when they do have caffeine, this combination of 4 hours of sleep and 20 hours of studying actually leads to better performance because the participants do actually benefit from their 20 hours of studying. And this dot that used to be down here goes up here. It used to be 56, but now it's 86. So here we have a three-way interaction because the caffeine is causing the interaction between hours of studying and hours of sleep to disappear. It's causing this interaction that we see over here to no longer exist over here. That's what a three-way interaction is. Here's one way to think about it. Remember we said that an interaction is when the effect of an independent variable depends on the level of the other independent variable. We see that right here because what we're seeing right here is that this effect of hours of studying depends on the hours of sleep because the two lines don't look the same. What a three-way interaction is when the interaction between two independent variables actually depends on a third independent variable. What I'm trying to explain is that this idea of an interaction is just the idea that it depends. With this basic type of interaction that we covered first, it's when the effect of an independent variable depends on the level of another independent variable, and the lines aren't parallel. But a three-way interaction is when actually when the interaction itself depends on the level of a third independent variable. Now let's look at some examples of what would be a three-way interaction and what wouldn't be a three-way interaction. First, I'll go over a couple examples with you right now. If this graph, this interaction that we see here, also appeared over here, and the two graphs look the same, then the interaction wouldn't depend on the level of IV3. It would be the same at both levels of IV3, and that would be no three-way interaction. Also, if both graphs looked like this, meaning if both graphs had parallel lines with no interaction here and no interaction here, that would again be no three-way interaction because the two graphs would be the same. Whenever the two graphs look the same, there's no three-way interaction. When they look different, there is a three-way interaction. So here's some examples. Here's two different types of three-way interactions. One is when you have an interaction at one level of IV3 and no interaction at the other level of IV3. Another example of a three-way interaction is when you have one type of interaction at the first level of IV3 and a different type of interaction at the other level of IV3. Because here you just have non-parallel lines, and here you actually have an X. Here are two types of no three-way interaction. If there's no interaction here and no interaction here, there's no three-way interaction because the two graphs are the same. if you have the same type of interaction at each level of IB3, it's no three-way interaction because, again, the two graphs look the same. Whenever the two graphs look different, there's a three-way interaction. Whenever the two graphs look the same, there's no three-way interaction. So what's the reason for doing an experiment with three independent variables is to look at whether you have a three-way interaction. And there's actually different results. There's actually a list of results that can be found in a three-way factorial design, meaning a three-way factorial design is an experiment with three independent variables. In this type of experiment with three independent variables, you can find a main effect of each independent variable. You can find some two-way interactions. A two-way interaction is just a basic interaction between two independent variables. It's a type of interaction we covered first. So you can have an interaction between IB1 and IB2, between IB1 and IB3, or between IB2 and IB3. These are all just interactions between two independent variables, which are two-way interactions. And you can have a three-way interaction, which is what we just talked about, which is when an interaction changes across the levels of a third independent variable. Now I'm going to show you how to look at the three main effects, how to look at the two-way interactions, and how to look at the three-way interaction. Let's start with the main effects. In a 2x2x2 factorial design, the main effects aren't quite as straightforward because it's not just the difference between the two column means and the two row means anymore. The main effect of IB1 would be the mean of all 8. The main effect of IB1 would be the difference between the mean of all 8 people who were assigned to the first level of IB1 and the mean of all 8 people who were assigned to the second level of IB1. In other words, the main effect of IB1, of hours of studying, would be the difference between the mean of all 8 people who were assigned to 10 hours of studying and the mean of all 8 people who were assigned to 20 hours of studying. So here we have 2 people here, 2 here, 2 here, and 2 here. All 8 of those people were assigned to 10 hours of studying. You have 2 people here, 2 here, 2 here, and 2 here. Those 8 people were all assigned to 20 hours of studying. The main effect of hours of studying would just be the difference between the mean of all 8 people who were assigned to 10 hours and the mean of all 8 people who were assigned to 20 hours. We can look at that right here. This is all 8 people who were in the 10-hour condition, all 8 people who were in the 20-hour condition. I got this mean by adding the 8 numbers and dividing by 8. I got this mean by adding the 8 numbers and dividing by 8. Since these two means are different, there is a main effect of hours of studying. The 10-hour mean is different from the 20-hour mean. The main effect of IB2, which is hours of sleep, would be the difference between the mean of all 8 people who were assigned to the first level of hours of sleep and the mean of all 8 people who were assigned to the second level of hours of sleep. In other words, it would be the difference between the mean of all 8 people in the 4-hour of sleep condition and the mean of all 8 people in the 6 hours of sleep condition. These 8 people in this entire top row up here are in the 4-hour condition. These 8 people in this entire bottom row are in the 6-hour condition. The main effect of IB2 is just the difference between the mean of these 8 people and the mean of all of these 8 people. We can look at that right here. Here's the mean of these 8 people. Here's the mean of these 8 people. The two means are different. So there is a main effect of hours of sleep. The 6-hour condition did better on the exam than the 4-hour condition, which is what we would expect. The mean of the main effect of IB3, or the main effect of caffeine intake, would be the difference between the mean of all 8 people who were assigned to the first level of IB3 and the mean of all 8 people who were assigned to the second level of IV3. In other words, it would just be the difference between the mean of the 8 people in the 0 milligram condition and the mean of the 8 people in the 100 milligram condition. We can look at that right here. This mean, the mean of these 8 people, is higher than the mean of these 8 people. So we do have a main effective caffeine dose. The 8 people who had caffeine did better on average than the 8 people who didn't have caffeine. So we've already found out that we have 3 main effects. Each independent variable had a main effect here. Now we can look at the two-way interactions between IV 1 and 2, 1 and 3, and 2 and 3, right here. If we want to look at the two-way interaction between IV1 and IV2, we actually have to eliminate the third independent variable and actually turn the design back into a 2x2 design, in which IV1 and IV2 are the 2 independent variables. This is how we would do that. We would create this type of a grid here, where we have the 2 levels of studying and the 2 levels of sleep, and each of these 4 cells includes all 4 people who were assigned to the combination of so right here we have, in this cell, we have all 4 people who experienced 10 hours of studying and 4 hours of sleep. Here we have all 4 people who had 20 hours of studying and 4 hours of sleep. Here we have 4 people who were assigned to 10 hours and 6 hours. And here we have the 4 people who were assigned to 20 hours and 6 hours. And this cell mean right here is actually the mean of all 4 people in here. This cell mean is the mean of all 4 people. This is the mean of all 4 people, and this is the mean of all 4 people. So each cell mean was calculated by adding the 4 values inside each cell and dividing the total by 4. The reason why I made this a dotted line is to show that these 4 people are all in the same cell now. There's actually a technical term for what I've done here. It's called collapsing one of the independent variables. When you collapse an independent variable, you're pretending that independent variable was never there. I've collapsed the third independent variable of caffeine dose, and I've made it back. I made the experiment back into a 2x2 design with 2 independent variables. Now I can just plot the 4 cell means in a graph, like I did with the 2x2 design, and see if the lines are parallel. If they're parallel, there's no interaction between IVs 1 and 2. If they're not parallel, there is an interaction between IVs 1 and 2. These aren't completely parallel because in the top row, this goes up by 10, and in the bottom row, this goes up by 20. So this is going up by 10, this is going up by 20. They're not parallel, so there is an interaction here between IVs 1 and 2. If you want to look at the interaction between IVs 1 and 3, we have to collapse the second independent variable of hours of sleep and make a 2x2 design. That's what I did here. Now the columns are the 2 levels of studying, and the rows are the 2 levels of caffeine dose. And we have 4 cells. Each cell mean is just the mean of the 4 people in the cell. We can plot the 4 cell means in a graph and see if they're parallel. They're not parallel because this goes up by 10, this goes up by 15, and actually the lines cross, so they're definitely not parallel. So we do have an interaction between hours of studying and caffeine dose in this graph. The effect of hours of studying is with 0 milligrams of caffeine is different than the effect of hours of studying with 100 milligrams of caffeine. Because it looks like with 100 milligrams of caffeine, studying 20 hours really helps you. The mean goes up by, it looks like 25 actually. but it doesn't when you don't have caffeine. Uh, the mean only goes up by 10 in the 20-hour condition. It goes up from 66 to 76, which isn't as big of an effect of studying. Now we can collapse the first independent variable, which is hours of studying, and just look at the interaction between sleep and caffeine dose. Now we have the two levels of sleep here and the two levels of caffeine here. Each cell mean is the mean of the 4 values in the cell divided by, each cell mean is the total of the 4 values in the cell divided by 4. Because each cell mean is just the mean of the 4 values inside the cell. When we plot these 4 cell means, they're not parallel. So we do see an interaction between hours of sleep and caffeine dose between IVs 2 and 3. What this looks like is that when you have little sleep and no caffeine, you do really poorly. The mean is 56. When you've had 6 hours of sleep, your score is pretty high, regardless of whether you had caffeine or no caffeine, because 6 hours of sleep and 0 milligrams had a high average, and 6 hours and 100 milligrams had a high average. They're both 86. In this graph, it actually looks like the only group that's doing poorly is these 4 people who had both no caffeine and 4 hours of sleep, which makes sense. So far we found all 3 main effects were there, and all 3 two-way interactions were there. There was an interaction between IVs 1 and 2, between 1 and 3, and between 2 and 3. And we already looked at the 3-way interaction at the beginning. But let's look at it one more time. In order to see if there's a 3-way interaction, you have to go back to this grid where each cell includes 2 people, and you're looking at all 8 cells. And this grid is the first level of IV3. This grid is the second level of IV3. And you plot these 4 cell means in a graph, and these 4 cell means in a graph. And if we see this outcome that we see here, where we have an interaction at one level of IV3, but no interaction at the other, that is a certain type of 3-way interaction. Because this graph and this graph don't look the same, which means that there is a 3-way interaction. Technically, there's no limit to the number of independent variables that an experiment can have, even though most experiments won't include more than 3 or 4 independent variables. We could have included a 4th independent variable in this experiment and made it into a 2 by 2 by 2 by 2 factorial design. In that case, the experiment would have had 16 cells, or 16 conditions. If we did do a 2 by 2 by 2 by 2 factorial design, we could look at whether the 3-way interaction changes across the levels of the 4th independent variable. If the 3-way interaction does change across the levels of the 4th independent variable, then we would have a result called the 4-way interaction. We won't get into the details of that, but I just wanted to mention that it would be possible to do an experiment with a 4th independent variable and then look to see if we find a 4-way interaction.